Yeah, it started. You can start.
Yes, sir. Yes, sir. Good morning, everyone. Welcome to day 4 of our faculty development program, sponsored by AICTE and conducted by Department of Nanoscience and Technology, Bharathiar University. Today we have Professor Dr. M.Sathish from CSIR Secretary joining us today again. Yesterday we had the great opportunity of listening to his lecture, and as we are already introduced with him, without further ado, I welcome Dr. M.Sathish to deliver his talk. Thank you.
Yeah, thank you. Uh, okay, I'll share my slides. Yeah, can you see my slides, right?
Yes, sir. Yes, sir.
Yeah. So I once again thank Professor Ponpandian and his team and the department and the Bharathiar University for the opportunity to again share my some of my research. I hope this may be interesting for some of you. I think I have introduced our institute yesterday itself, so maybe just I'll go quickly on these two parts. Since some of you may be new, then maybe we can again just refresh. We have 6 departments, but the common interest in all, we cover both physics, chemistry, and engineering, and even some biology also, and we, of course the material science. But the common interesting point is here the electrochemistry. So wherever the electrochemistry involved, whether it's a metallurgy or engineering, or it may be a chemistry or to core the physics, we have a department. And then we do have opportunity for MSc and MPhil students for their final year project. They can spend some maybe maximum of 1 year. In the case of MTech or even MPhil students can they stay up to 1 year. MSc students, depending on their project duration, they can stay for 6 months or 3 months. Of course, they have to apply through a proper channel. That means the application has to be forwarded through the head of the department to our concerned department. So if somebody may be interested, then you can go here and then you can see here, this is academic column. Then you can go to the dissertation guidelines. There are information is available. So coming back to research area, yesterday I have shown these slides. So we were working on basically materials aspects. Of course, our core interest is to make supercapacitors and photocatalytic hydrogen production. So as I told you earlier, we are making layered materials, particularly 2D layered materials or metal oxides by using supercritical fluids. So these are one of the unique technique, particularly for the material synthesis in a short reaction time. So the other side, we also do metal oxides or sulfide synthesis, either it's a conventional way or by using a supercritical fluids for all solid state battery as well as some photocatalytic applications. We do work on carbon-based materials, particularly for supercapacitors. And one of the unique thing is the liquid-liquid interface. Maybe what I thought was today, since I put my title is role of carbon materials in the electrochemical energy storage devices, I thought of cover little bit on this liquid-liquid interface. So some of you may be interesting for some of you. And then this, I will move on to the next part. I will move on to the carbon-based materials for particularly lithium-ion batteries as well as supercapacitors. Since already you had a brief talk about the supercapacitor by one of my colleague as well as the other colleague was maybe he introduced you to what is lithium-ion battery. So I don't want to go into the details of what is lithium-ion battery or what is supercapacitors. Maybe I'll tell how these carbon-based materials are playing a role. Coming back to the fullerene nanostructures, what I was talking about is, for example, fullerene nanotubes or nanorods. So this top one is a carbon nanotubes. The carbon nanotubes is made up of carbon atoms. Okay, so this is a single carbon layers. Maybe you can open up. If you cut these tubes, then you will end up with a graphene sheet. So if you fold it, this is a single wall carbon nanotubes. multiple carbon nanotubes, in the sense there may be another 2 layers or 3 layers, or maybe the number of layers will keep on increases. Okay, so this is called carbon nanotubes. This maybe we are aware, we have come across. But fullerene nanoviscous are relatively, I cannot say it is new, but it's not much visibility, I could say. Okay, so this looks like these tubes looks like carbon nanotubes, but these walls are made up of individual C60 molecules. So here basically what we are doing is we are self-assembling these C60 molecules into a tubular form or a rod-like form or a sheet-like form by using this liquid-liquid interfacial preparations. So we can use both C60 and C70 and C60 derivatives or C70 derivatives. Only the requirement is this particular compound or this C60 or C70 or its derivatives should be soluble in one solvent. So it has to be completely soluble. Many of the carbon, for example, carbon nanotubes, you cannot make it soluble unless otherwise you functionalize it, or even if you physically bear carbon nanotubes, it's not possible to dissolve. You can only disperse. Okay. So the physical appearance of fullerene nanoviscous are very similar to the carbon nanotubes, but the fullerene nanoviscous contains thick wall and exist both tubular and non-tubular structures. Okay, so the first we have reported this fullerene nanoviscous in 2002 by Miyazawa. So he is one of the pioneer in C60 nanostructure based materials. So to whom I was working for maybe 3 years as a postdoctoral fellow between 2006 to 2009. So actually, basically, he is a biology person. The background is biology, but somehow he was started working on material science. So since I am a first chemist as a postdoc in this group, so I have a lot of opportunity to explore this technique for some other to the next level. I can say I can take to the next level. Here, the one more interesting aspects of this liquid-liquid interface is we can change the aspect ratio of the fullerene nanoviscous by controlling the liquid-liquid interfacial potential or pressure or whatever it may be. There is a, if you mix two immiscible liquids, I hope you might be seen there is an interface. Okay, so we are doing the reaction at the interface. By tuning the interfacial property, you could also tune the morphology, size, shape, and the aspect ratio of the nanostructures. So that is one of the added advantage for this particular technique. So it may be easy for you to understand. For example, in the case, I simply this preparation is a very simple technique. Okay, only for the characterization you need advanced tools. For the material preparation, you have to buy only C60 or C70 or its derivatives. For example, here the C60 saturated solution. I hope chemists may be knowing that C60 molecules are it's a carbon-based materials. It has 60 numbers of carbon. Its structure is like football-like structures, but it is fortunately it is soluble in few solvents like benzene, carbon tetrachloride, or carbon disulfide. It will not solve in all solvents. It's selectively for few solvents it will get dissolved. Okay, so over there, so I just take maybe in a vial, I can add some 1 or 2 ml of C60 saturated solution, and then I can put the alcohol solution. It may be ethanol or butanol or N-butanol, or there are variety of alcohols we have, but at least we should have minimum of isopropyl alcohol or ethanol. Okay, so if you have, if you add the above the other alcohol solution slowly on the top, then you could form an interface. Okay, so this is called generally the formation of liquid-liquid interface. So if you ultrasonicate this solution and then keep it for maybe ultrasonication for 5 minutes, and then keep it this solution for 24 hours at maybe relatively 5 degrees Celsius or 10 degrees Celsius. I just put 5 degrees Celsius. Here we have the options to vary the temperature also, so that you can tune the nanostructures. So you will get like this, and then if you have after 1 or 2 days, then you could see there is a formation of nanostructures on the bottom of these tubes. Okay, here the solubility of the, we call it as a good solvent. So generally it's soluble in organic solvents, and then these C60 molecules as a good electron acceptor. Okay, so in might be seen that PCCM is generally used in solar cells. So these are C60 as it is, or its derivatives are good, well known for this electron acceptor property. And C60 itself can will take it, it will absorb the visible light. That's why you could see the previous slide, I put some color for the C60 solution. So this is a, even if you dissolve in some solvent, you could see some colored solution. That means it could absorb the visible light. So there are some unique application for the C60 molecules. For example, if you want highly pure carbon, I'm talking about for high-end applications where you are looking for pure carbon atoms without any metal impurities or any salt. Then if you could able to take the C60 molecule and then you can carbonize it, you can end up with a highly pure carbon material. Of course, this is a too expensive process, and then most of the time it's we cannot afford it. Okay, so wherever you need high-end applications like pure carbon, then it is, this could be done. Also, this fluorine nanoviscous could be tuned. The size as well as the morphology could be tuned. Fluorine nanoviscous, whereas these are not possible for the carbon nanotubes. Okay, the fluorine nanotubes, since it's made up of C60 molecule, you can dissolve in some solvent, but this carbon nanotubes you cannot. Okay, so the carbon nanotubes can accept electrons, but it cannot act as a visible light absorption material. And then you can, carbon nanotubes always comes with some amount of impurities, particularly metal or iron or cobalt based materials, since this has been used as a catalyst when for making a carbon nanotubes. And then you cannot tune the carbon nanotube size easily, also the morphology. Here actually some of the glimpse. So using this liquid-liquid interface, we have made a nanoporous fluorine nanoviscous. We have also made nano sheets, but that could be tunable size. And then we can do some metal incorporation into the nanoviscous. And then we can also make some bundled nanoviscous. That means that 10-15 nanoviscous to be bundled. Or you can also make a three-dimensional cubes. Okay. I just explained, I give some 1 or 2 examples for each cases. So this is a first examples for the nanoporous nanoviscous. We call it as a fluorine nanoviscous. So since you can see, this is a simple SEM image shows that tubular, this is a many viscous-like morphology. Okay, here you could see we add some 2 ml of C60 saturated benzene solution. Over there, I can add some isopropyl alcohol at 5 degrees Celsius. Just ultrasonicate for a minute and then keep it for 24 hours. You can see some small cotton-like precipitate after 1 or 2 days. Okay, this is very spongy-like precipitate. Even you can just take this precipitate by using your forceps. Okay, so if you dry it, then you could see this kind of viscous. This looks like exactly like a cotton that was generally in fly in the air. Okay. So if you see closely, look the morphology or the structure of this in high resolution TEM, you could see there is a white patches. Okay, so that is nothing but the porous. So these tubes are maybe around 230 nanometers. So this the size of the thickness of these tubes around 230 nanometers. There is a 65 nanometers goes to the wall, and then the rest is 100 nanometers goes to as a tubular structure. Also, we could see some non-tubular formations. It's a mixing of tubular and non-tubular. Of course, you could able to selectively make a non-tubular structure as well as the tubular structures by changing the volume, the ratio. For example, here I 2:9 I added. Instead of 1:9, if you add, this morphology will be the tubular structure. It may be a tubular or it may be a non-tubular, but also the size can also be controlled by changing the nature of the alcohol. Instead of isopropyl alcohol, if I use butanol, then I could get only a rod. Instead of wires, I can get only a rods. Okay. The specific surface area of the materials is 376 meters square per gram. Generally, fullerene nanoviscous are prepared by having, instead of benzene, people will use toluene isopropyl alcohol. In such a case, I get this kind of rods, but without this porosity. I showed you some porosity. So those pores are options. We generally call it as a fullerene nanoviscous. But what we are talking about, nanoporous fullerene nanoviscous. So you could see the difference. Here the just fullerene nanoviscous has 26 meters squared per gram, whereas nanoporous fullerene nanoviscous has 376 meters squared per gram. So as I told you, you can get you can have both tubular and non-tubular. This is FCC crystalline in structure. So here you could see this. I told you about the wall thickness. You can see the really high resolution TEM. It could really show you what is the thickness of these walls and then how the porosity exists. Whether it exists only at the end or it may be throughout the tubes. So the other side, what we have done is seats. Okay. So here you could see the benzene ring-like structure. So the background is a mesh. Okay. Don't confuse with the mesh. So the background is a grids. Generally, we use it for TEM measurements. So the background. Over there, you can see the transparent benzene-like rings. Right here, there is one. Here, there are two. So these seats are made up of C60 molecules. So here we use carbon tetrachloride. I think the C60 saturated carbon tetrachloride and isopropyl alcohol. Then you will get such kind of seats. Whereas I keep the carbon C60 saturated carbon tetrachloride. I use instead of isopropyl alcohol, if I use ethanol, still I could able to get some small nano seats. If I go for methanol, and then these, as I told you, here you can get some nano seats, but not all. There are some unusual structures also have been formed. So that's why we generally we thought that minimum ethanol is required. And then if you go for isopropyl alcohol, carbon butanol or N-butanol or tertiary butyl alcohol, we have changed the alcohol nature. Okay. And then here also you could see there is a porosity. You could see this is a TEM image. So these are the SEM images. We use the TEM grid in the SEM machine. We use it in STM mode. Okay, these images have been taken in STM mode. Here you can see this TEM mode. The same grid has been used here. You could see this benzene ring-like sheets. Okay, so that also has pores. But the other side you can see kind of rod-like structures are highly transparent sheet, but here you can see similar like flower-like structure. Here there is a rod-like structure. So here these rods, these sheets has been some bending. So what we observed is there is a high surface energy since these nano sheets are stored in a solution. When you dry it for over the TM grid, what will happen is this solvent evaporate. So there is a surface energy also increases. So in order to avoid the high surface energy, these sheets undergoes a rolling. Okay, so it will undergo the rolling so that the surface of this of the sheets may be reduced. Okay, that exposure of more surface will be reduced. That is generally possible. That is occurs in all the sheets like structures. Unless otherwise you have some surfactant molecule to stabilize these surface are very reactive, or it may be it want to reduce this active surface area, so it will roll up. So because of this, we could see some kind of rolled sheets. Okay. So the number of carbon atoms and polarity of the alcohols plays a major role on the particle size variation. So here we just simply change the alcohol nature. We could able to tune the size of the sheet, but still all these cases are sheets. Interestingly, the same system, when I use carbon tetrachloride and isopropyl alcohol, I got a benzene-like structure. Okay, the sheets are formed, but all the sheets are like benzene-like shapes. Okay, when I use C60 saturated solution is made up of toluene and the tertiary butyl alcohol. Okay, that means instead of carbon tetrachloride, I use benzene, toluene. Instead of isopropyl alcohol, I use the tertiary butyl alcohol. Okay, then I could able to get this kind of rhombohedral sheets. Still, these are sheets. If you see the thickness, so these are maybe a few nanometers, maybe 10 to 20 nanometers. But the shape is all the shapes is not only one. Okay, all the sheets are in rhombohedral in shape. Whereas when you use a benzene C60 saturated solution, as like the previous case, we use benzene and isopropyl alcohol, then you will get a rod or the nano-viscous. Whereas when I use the benzene and tertiary butyl alcohol, and then I could get only these sheets, but here the surprising thing is not uniform sheets. Here I get what only hexagonal sheets, it's a rhombohedral hydride sheets. Here I can get mixture of sheets. Even I can see that's a triangle-like or square-like or all the shapes. Okay, so all these shapes are mixed up here. So more interestingly, if I make this interface and then I make a hexagonal sheets and then this rhombohedral sheets or mixture of sheets, when I put these sheets over the water, okay, when I disperse these sheets over the water, these sheets are very stable. Whereas the sheets is made up of tertiary butyl alcohol, is when I put it over water, this undergoes a deformation and then converted into a completely nanorods, not a rolled sheet. These rods are not a rolled sheets, it's a completely nanorods. Okay, that means the breaking of, actually I am sorry, I didn't have this detailed presentation that is of this particular study. Maybe if some of you interested, maybe you can go to this paper, maybe you can find out more details how this deform into a nanorods over a time. When you just put the sheets over the water. Here the reason behind this, I don't think I have it the slides. So here there is a porosity. I was talking about the previous slide. There is a porosity in the sheets. Okay, so these pores are very nanopores. Okay, there are nanometer in size. Whereas the other case, we do observe a pores. This case, rhombohedral as well as this mixed sheets, we do observe a pores, but the pores are maybe a few Armstrong thick. Okay. So when you put water, okay, so C60 molecules is highly hydrophobic in nature. Okay, so that hydrophobic in the sense it will repel to the water. So these nanopores doesn't allow this water to enter inside these C60 seeds. So the structure is stable. Whereas here I can see this is the pores are really huge when compared to these pores, so that the water molecule can enter into the pores. So because of the force in the repulsion force inside the porosity of the material, this will breaks into a nanorods. So this transformation is not occurs immediately, it will occur after a day. So slowly this structure disappears and then you could end up with a nanorods. So this is a reason which we have proved for this particular transformation. So we call it as a shape control. We can also control the shape.